This course provides an introduction to the concepts and devices associated with solid-state electronic circuitry. It also discusses the construction and operation of various types of semiconductor devices, including p-n junction diodes, bipolar transistors, FETs, UJTs, SCRs, and triacs. All solid-state electronics is based on the properties of a crystalline structure. Modifications to this basic structure create the semiconductor devices that are the basis of solid-state electronics. To understand how semiconductors work, we need to look at their composition and nature. A semiconductor is created from silicon or germanium. Quantitative process measurement provides information on how much of each component is in the sample. Silicon is used more than germanium because of its ability to withstand heat. Since pure silicon is a perfect insulator, impurities are added to make the silicon act as a conductor. By adding impurities or doping, the silicon can be changed to N material with an excess of negative charges or P material with an excess of positive charges. By applying external energy to these materials, we can force these charges to move. In this example, a battery provides the electrical potential needed to cause flow in this N material. Conduction in semiconductor material is similar to conduction in a copper wire. With voltage applied across the material, negative charges or electrons move through the crystal just as they would move through wire. The positive potential of the battery attracts negative charges in the crystal. Recall Kirchhoff's law of current. No more current may arrive at one point than leaves that point in a series circuit. In N material, negative charges or electrons are the majority carriers. Conduction or charge flow through P material is by positive charges or holes. They are called holes because they represent a lack of material or electrons. Repelled by the battery's positive potential, a steady stream of holes moves toward the battery's negative potential. So in P, or positive material, holes are the majority carriers. Because the operation of the semiconductor is dependent on its physical properties, heat is a factor that must be controlled. Heat increases the amount of energy in the material. Too much heat can destroy the crystalline structure of the semiconductor. Most of the semiconductor devices you'll be working with are rated for specific temperature operating ranges. Within these constraints, you can expect them to perform to high standards for long periods of time. Understanding the structure and composition of P and N semiconductor materials makes it much easier to figure out how solid-state devices work. Semiconductor diodes are devices that permit current flow in one direction. Often diodes are used to change alternating current to direct current. Diodes consist of one region of N material and one region of P material. The area where the sections meet is called the junction. Let's look at how charge flows through a p-n junction. When the junction is formed, a few of the charges diffuse across the junction in pairs. This depletes the number of free charges in the area. The buildup of charged ions creates an electrostatic field that acts as a barrier to flow. A p-n junction by itself forms a diode, which is a two-electrode device. Let's see why current flows in only one direction. In this example, the positive terminal of a battery is connected to the N material, and the negative terminal is connected to the P material. This is known as reverse bias. With reverse bias, no significant current will flow. Reverse bias widens the depletion region, so there is high resistance to current flow. However, even with reverse bias, there is an insignificant amount of current called leakage in most applications. Application of reverse bias above the peak inverse voltage rating, or PIV, will cause leakage current to become significant and will generate enough heat to destroy the diode. The PIV rating must not be exceeded. Now let's look at an example of forward biasing, where current flows across the p-n junction. Here, the positive terminal of the battery is connected to the P material. The negative terminal of the battery is connected to the N material. Note that we have included an ammeter and a voltmeter to make it easier to see how forward biasing occurs. As voltage increases, the depletion region decreases. When there is no depletion region, current flows. As current increases, there is no further increase in voltage across the diode. Maximum forward current occurs when all forward biased carriers are utilized. Any further increase in voltage at this point will increase the voltage drop across the junction. This is called saturation. Operation above this maximum forward current for a period of time exceeding specifications will generate enough heat to permanently damage the diode. This is the schematic symbol for a PN junction diode. It indicates how the diode is connected in a circuit. The arrowhead indicates the anode region, which is made up of P material. The vertical line indicates the cathode region of N material. Now let's take a look at how diodes are used. Here is an example of a rectifier circuit, which converts alternating current to direct current. The components include a transformer, a diode, and a load resistor. The diode is connected as shown. Assume the polarity of negative to positive across the secondary of the transformer using the lower circuit leg as the reference. With voltage at this polarity, notice the negative is to the P material and the positive is to the N material. This is reverse bias. No current will flow. When polarity is reversed, the positive is to the P material and the negative is to the N material. Current will flow. An alternating current across the secondary will result in a wave shape across the resistor. Because current only flows during one alternation, this is called a half-wave rectifier. A half-wave rectifier produces pulsating direct current. Pulsating direct current goes from zero to peak current, but only positive or negative, not both, like alternating current. Another diode application is the full-wave bridge rectifier circuit. The components include a transformer, 4 interconnected PN junction diodes, and a resistor, which acts as the load. Let's trace the current flow through one complete cycle starting at point B. Assume a positive polarity at point A relative to point B. Current flows through D1 up through RL through D3. Through the secondary of the transformer and back to point B. Current cannot flow through D2 and D4 because they are reverse biased. 1/2 cycle later, the polarity across the secondary of the transformer reverses, forward biasing D2 and D4 and reverse biasing D1 and D3. Current flow is now from point A through D4, up through RL, through D2, through the secondary of the transformer, and back to point A. Proper biasing of each pair of diodes in the circuit makes full-wave rectification possible. This produces non-pulsating direct current. Note that current flows through each alternation.